To determine the correct circuit breaker size, we need to follow a few steps. Firstly, determine the size of the PVC conduit. The conduit in question is 1 inch in diameter. Secondly, identify the number of conductors. In this scenario, there are 3 current carrying conductors. Thirdly, calculate the fill percentage of the conduit. According to the National Electrical Code, NEC, the conduit should not be filled with more than 40% of its total cross-sectional area for conductors or cables. The cross-sectional area of a 1-inch conduit is approximately 0.44 square inches. Therefore, the maximum fill percentage for 3 conductors is calculated by dividing the total cross-sectional area of the conductors by the cross-sectional area of the conduits and multiplying by 100%. Assuming each conductor is number 12 American wire gauge (AUG), its cross-sectional area is approximately 0.7 square inches. So, the fill percentage is approximately 4.78%, which is calculated by multiplying 3 by 0.7, dividing by 0.44, and multiplying by 100%. Fourthly, it is important to check NEC requirements. The NEC requires that for 3 current carrying conductors in a single raceway, the current capacity of the circuit breaker shall not exceed 80% of the ampacity of the conductors. Fifthly, calculate the circuit breaker size. Based on the fill percentage and NEC requirements, you can calculate the maximum current capacity of the conductors. The fill percentage of 4.78% is less than 40%. Therefore, it is permissible to install 3 current carrying conductors in the conduit. The current capacity of each number 12 AWG conductor is approximately 20 amps. The maximum current capacity of the 3 conductors is 3 times 20 amps, which equals 60 amps. The circuit breaker size should not exceed 80% of the ampacity. The circuit breaker size is 60 amps times 0.8, which equals 48 amps. Therefore, based on the given information, a 48 amp circuit breaker would be required. To elaborate, let's consider the NEC guidelines in more detail. The NEC provides tables and articles that dictate how to properly size conductors, conduits, and overcurrent protection devices like circuit breakers. One critical aspect is conduit fill. The NEC specifies the maximum percentage of a conduit's cross-sectional area that can be occupied by conductors. This limit prevents overheating and ensures that conductors can be easily pulled into and out of the conduit. The 40% fill rule applies when there are 3 or more conductors in a conduit. For a 1-inch PVC conduit, the internal area is approximately 0.864 square inches, but the usable area is reduced due to the fill percentage limitation. When calculating the conduit fill, you need to consider the actual cross-sectional area of the conductors, including their insulation. This information can be found in NEC Chapter 9, Table 5a. For number 12 AWG conductors with common insulation types like THHN or THWN, the approximate area is 0.133 square inches per conductor. With 3 number 12 AWG conductors, the total area occupied is 3 times 0.133 square inches, which equals 0.399 square inches. To determine the fill percentage, divide the total conductor area by the conduit area and multiply by 100%. In this case, it would be 0.399 divided by 0.864 multiplied by 100%, resulting in approximately 4.62%. This is well below the 40% limit, so the conduit fill is acceptable. Next, consider the ampacity of the conductors. Ampacity refers to the maximum current a conductor can carry continuously without exceeding its temperature rating. The NEC provides ampacity tables such as Table 310.15b16 that lists the ampacity of conductors based on their size, insulation type, and temperature rating. For number 12 AWG copper conductors with THHN insulation, the ampacity is typically 30 amps at 90 degrees Celsius, but is often limited to 20 amps due to termination temperature limitations of the connected equipment, as per NEC 110.14 cone. When multiple current-carrying conductors are installed in a raceway or cable, their ampacity may need to be directed to account for the increased heat generated. NEC Table 310.15 provides adjustment factors for ampacity based on the number of current carrying conductors in a raceway. In this scenario, with 3 current carrying conductors, the dirting factor is not required since there are only 3 current carrying conductors. The table indicates no dirting is necessary for 3 or fewer conductors. Finally, select the appropriate circuit breaker size. The circuit breaker protects the conductors from overcurrents caused by short circuits or overloads. The NEC requires that the circuit breaker rating not exceed the ampacity of the conductors it protects. In this case, the number 12 AWG conductors are rated for 20 amps due to terminal limitations. Therefore, the maximum circuit breaker size is 20 amps. The 80% rule is applied to continuous loads. If the load is considered continuous, meaning it operates for 3 hours or more at a time, the circuit breaker should be sized no larger than 80% of its rating. However, if the load is not continuous, the circuit breaker can be sized up to the conductor's ampacity, but in no case more than the equipment's listing. Since the conductor ampacity is 20 amps, the maximum breaker size is 20 amps. However, the provided answer incorrectly calculates this, and then applies the 80% rule incorrectly as well, leading to an incorrect answer. In summary, the steps to determine the correct circuit breaker size are: firstly, determine the conduit size and conductor count. Secondly, calculate the conduit fill percentage to ensure it meets NEC requirements. Thirdly, determine the ampacity of the conductors, considering any dirting factors. Fourthly, select a circuit breaker that does not exceed the conductor ampacity and is appropriate for the type of load being served. This ensures a safe and compliant electrical installation. Now, let's delve deeper into the NEC requirements and calculations to further clarify the process. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations. It is updated every 3 years to reflect changes in technology and best practices. Understanding the NEC is crucial for anyone involved in electrical work, as it helps ensure safety and compliance with regulations. When sizing circuit breakers and conductors, it is essential to refer to the specific NEC articles and tables that apply to the installation. For example, Article 310 covers conductors for general wiring, while Article 344 covers rigid metal conduit, and Article 352 covers rigid polyvinyl chloride conduit, or PVC. These articles provide detailed information on conductor types, ampacities, conduit fill requirements, and other relevant factors. One of the key concepts in electrical calculations is ampacity dirting. As mentioned earlier, when multiple current carrying conductors are installed in a raceway or cable, their ampacity may need to be reduced to prevent overheating. This is because the heat generated by the conductors can build up inside the raceway, increasing the conductor temperature and potentially damaging the insulation. NEC Table 310.15 provides adjustment factors for ampacity based on the number of current carrying conductors in a raceway. The more conductors there are, the greater the dirting factor. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its original value. If there are 7 to 9 conductors, the ampacity must be reduced to 70%. It is important to note that the dirting factors apply only to current carrying conductors. Grounding conductors and equipment grounding conductors are not considered current carrying conductors for the purposes of ampacity dirting. Another important consideration is voltage drop. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, current, and resistance. The formula for voltage drop is voltage drop equals current times resistance. The resistance of a conductor depends on its material, size, and temperature. The NEC provides tables that list the resistance of different types of conductors. When sizing conductors, you need to ensure that the voltage drop does not exceed the recommended limits. If the voltage drop is too high, you may need to increase the conductor size or reduce the length of the circuit. In addition to conduit fill, ampacity darting, and voltage drop, there are other factors to consider when sizing circuit breakers and conductors. These include the type of load being served, the ambient temperature, and the presence of harmonics. Different types of loads, such as motors, lighting, and heating equipment, have different characteristics that can affect the sizing of circuit breakers and conductors. For example, motors typically draw a high inrush current when they start, so the circuit breaker must be sized to accommodate this inrush current. The ambient temperature can also affect the ampacity of conductors. The NEC ampacity tables are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this, the ampacity of the conductors must be derated. Harmonics are distortions in the electrical waveform that can cause overheating of conductors and equipment. If harmonics are present, the conductors and circuit breakers may need to be oversized to compensate for the increased heating. In summary, sizing circuit breakers and conductors is a complex process that requires a thorough understanding of the NEC and electrical principles. It is essential to consider all relevant factors, such as conduit fill, ampacity darting, voltage drop, load type, ambient temperature, and harmonics, to ensure a safe and compliant electrical installation. By following the NEC guidelines and using sound engineering judgment, you can protect people and property from electrical hazards. Let's expand on the practical application of these concepts with some examples. Consider a scenario where you are installing a new branch circuit to supply power to a kitchen appliance. The appliance is rated for 12 amps at 120 volts. The circuit will be wired with number 12 AWG copper conductors with DHHN insulation. The circuit will run through a 1/2-inch PVC conduit. The first step is to determine the number of current-carrying conductors. In this case, there will be two current-carrying conductors, a hot conductor and a neutral conductor. The grounding conductor is not considered a current-carrying conductor for the purposes of ampacity darting. Next, calculate the conduit fill percentage. The 1/2-inch PVC conduit has an internal area of approximately 0.304 square inches. The number 12 AWG conductors with THHN insulation have an area of 0.133 square inches each. The total area occupied by the two conductors is 2 times 0.133 square inches, which equals 0.266 square inches. The fill percentage is 0.266 divided by 0.304, multiplied by 100%, which equals approximately 8.75%. This is well below the 40% limit, so the conduit fill is acceptable. Now, determine the ampacity of the conductors. The number 12 AWG copper conductors with THHN insulation have an ampacity of 30 amps at 90 degrees Celsius, but are limited to 20 amps due to terminal temperature limitations. Since there are only two current-carrying conductors, no ampacity darting is required. Finally, select the appropriate circuit breaker size. The circuit breaker should be sized no larger than the ampacity of the conductors, which is 20 amps. However, the appliance is rated for 12 amps, so a 15-amp circuit breaker would be sufficient. It is important to check the NEC requirements for the specific type of appliance being served. Some appliances, such as motors, may require a larger circuit breaker to accommodate the inrush current. In another example, consider a scenario where you are installing a new feeder to supply power to a subpanel. The subpanel will serve multiple branch circuits with a total calculated load of 80 amps. The feeder will be wired with number 3 AWG copper conductors with THHN insulation. The feeder will run through a 1/4-inch rigid metal conduit. The first step is to determine the number of current-carrying conductors. In this case, there will be 3 current-carrying conductors, 2 hot conductors, and a neutral conductor. The grounding conductor is not considered a current-carrying conductor for the purposes of ampacity darting. Next, calculate the conduit fill percentage. The 1/4-inch rigid metal conduit has an internal area of approximately 1.50 square inches. The number 3 AWG conductors with THHN insulation have an area of 0.819 square inches each. The total area occupied by the 3 conductors is 3 times 0.819 square inches, which equals 0.2457 square inches. The fill percentage is 0.2457 divided by 1.50 multiplied by 100%, which equals approximately 16.38%. This is well below the 40% limit, so the conduit fill is acceptable. Now determine the ampacity of the conductors. The number 3 AWG copper conductors with THHN insulation have an ampacity of 100 amps at 90 degrees Celsius. Since there are only 3 current carrying conductors, no ampacity darting is required. Finally, select the appropriate circuit breaker size. The circuit breaker should be sized no larger than the ampacity of the conductors, which is 100 amps. However, the total calculated load of the subpanel is 80 amps, so a 90 amp circuit breaker would be sufficient. It is important to consider the potential for future load growth when sizing the feeder and circuit breaker. If there is a possibility that the load will increase in the future, it may be wise to oversize the feeder and circuit breaker to accommodate the additional load. These examples illustrate the practical application of the NEC requirements and electrical principles discussed earlier. By following these guidelines and using sound engineering judgment, you can ensure a safe and compliant electrical installation. Let's shift our focus to the specific types of conductors and conduits mentioned and the factors that influence their selection. Conductors are the pathways for electrical current. They are typically made of copper or aluminum, each with its own advantages and disadvantages. Copper has higher conductivity than aluminum, meaning it can carry more current for a given size. Copper is also more resistant to corrosion and has better mechanical strength. However, copper is more expensive than aluminum. Aluminum is lighter and less expensive than copper, making it a cost-effective option for larger conductors. However, aluminum has lower conductivity and is more susceptible to corrosion. When selecting conductors, it is important to consider the ampacity, voltage rating, and insulation type. The ampacity must be sufficient to carry the expected current without overheating. The voltage rating must be greater than or equal to the voltage of the circuit. The insulation type must be suitable for the environment in which the conductor will be installed. Common insulation types include THHN, THWN, XHHW, and use. THHN is a thermoplastic high heat resistant nylon coated insulation commonly used for dry locations. THWN is a thermoplastic heat and water resistant nylon coated insulation suitable for wet locations. XHHW is a cross-linked polyethylene high heat and water resistant insulation commonly used for both wet and dry locations. Use is an underground service entrance cable suitable for direct burial in the earth. Conduits are raceways that protect conductors from physical damage and provide a path for pulling conductors. Common types of conduits include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and rigid polyvinyl chloride conduit. Rigid metal conduit, or RMC, is a heavy-walled steel conduit that provides excellent protection against physical damage and corrosion. It is typically used for underground installations and in areas where there is a high risk of impact. Intermediate metal conduit, or INC, is a lighter weight steel conduit that provides good protection against physical damage and corrosion. It is typically used for above-ground installations in commercial and industrial buildings. Electrical metallic tubing, or EM, is a thin-walled steel conduit that is easy to bend and install. It is typically used for above-ground installations in residential and commercial buildings. Flexible metal conduit, or FMC, is a flexible steel conduit that allows for easy bending and movement. It is typically used for connecting motors and other equipment that may vibrate or move. Rigid polyvinyl chloride conduit, or PVC, is a non-metallic conduit that is resistant to corrosion and chemicals. It is typically used for underground installations and in areas where there is exposure to corrosive substances. When selecting conduits, it is important to consider the environment in which the conduit will be installed. For example, If the conduit will be exposed to corrosive substances, PVC conduit may be the best choice. If the conduit will be subject to physical damage, RMC or IMC may be more appropriate. It is also important to consider the fill capacity of the conduit. The NEC specifies the maximum number of conductors that can be installed in a given size of conduit. This is to prevent overheating and to ensure that conductors can be easily pulled into and out of the conduit. In addition to conductors and conduits, there are other components that are essential for electrical installations. These include circuit breakers, fuses, switches, receptacles, and lighting fixtures. Circuit breakers and fuses are overcurrent protection devices that protect conductors and equipment from damage caused by short circuits or overloads. Switches are used to control the flow of electricity to lighting fixtures and other equipment. Receptacles are used to provide a connection point for electrical appliances and devices. Lighting fixtures provide illumination for buildings and other spaces. When selecting these components, it is important to consider their voltage rating, current rating, and environmental rating. The voltage rating must be greater than or equal to the voltage of the circuit. The current rating must be sufficient to handle the expected load. The environmental rating must be suitable for the environment in which a component will be installed. By carefully selecting conductors, conduits, and other components, you can ensure a safe and reliable electrical installation. Always follow the NEC guidelines and use sound engineering judgment to protect people and property from electrical hazards. Finally, let's address some common misconceptions and frequently asked questions about circuit breaker sizing and conductor selection. One common misconception is that it is always better to oversize circuit breakers and conductors. While it may seem like oversizing provides extra safety margin, it can actually be dangerous. If a circuit breaker is too large for the conductors it protects, it may not trip in the event of an overload, allowing the conductors to overheat and potentially cause a fire. Another misconception is that the NEC is just a set of rules that must be followed blindly. While it is important to comply with the NEC requirements, it is also important to understand the underlying principles and reasoning behind the rules. This allows you to make informed decisions and apply the NEC appropriately in different situations. A frequently asked question is how to handle situations where the calculated circuit breaker size is not a standard size. For example, if the calculated circuit breaker size is 17 amps, the next standard size is 20 amps. In this case, the NEC allows you to round up to the next standard size, provided that the circuit breaker does not exceed the ampacity of the conductors. Another frequently asked question is how to handle situations where the load is likely to increase in the future. In this case, it may be wise to oversize the conductors and circuit breaker to accommodate the future load. However, it is important to avoid oversizing excessively, as this can lead to other problems such as increased cost and reduced efficiency. It is also important to consider the potential for energy efficiency when sizing electrical systems. By using energy-efficient lighting fixtures, appliances, and equipment, you can reduce the load on the electrical system and save money on energy bills. In addition, it is important to properly maintain electrical systems to ensure that they operate efficiently and safely. Regular inspections and maintenance can help identify and correct potential problems before they lead to costly repairs or hazardous conditions. In conclusion, circuit breaker sizing and conductor selection are critical aspects of electrical installations that require a thorough understanding of the NEC and electrical principles. By following the NEC guidelines, using sound engineering judgment, and addressing common misconceptions, you can ensure a safe, reliable, and energy-efficient electrical system.